Welcome back to another deep dive.
Yeah.
Today, I want to start with a question that, honestly, keeps me up at night.
Oh, yeah.
Not literally, I sleep fine,
Yeah.
but philosophically, it's a little unsettling. How does a machine, a pile of metal, silicon, plastic, and wires, actually know anything?
That's the fundamental question of artificial intelligence, isn't it?
It really is. Because think about it. We take our own senses for granted. I open my eyes, I see a microphone, I know I'm in a studio. It feels immediate. But a robot, it doesn't have eyes. It has cameras that just spit out a grid of pixel numbers. It doesn't have ears. It has a diaphragm measuring air pressure.
Oh.
So how on earth does it go from that noisy, messy data to saying, I am in the hallway, or you just asked me to turn on the lights?
It is a massive leap. And the answer is that, well, strictly speaking, it doesn't know. Not in the way we think of knowing as a certainty.
That's comforting. So my Roomba is just guessing its way through life.
We all are, to some extent. But for an AI, the world isn't a place of hard facts. It's a place of probabilities.
Hello.
It's just a noisy mess, and the AI is basically a professional gambler.
A gambler.
Yeah, constantly betting on what it thinks is happening based on the evidence it has.
And that is exactly what we're unpacking today. We have this fascinating stack of lecture materials here from California State University, Channel Islands.
Right.
We're looking at their AI modules. And we're going to be tackling some concepts that sound incredibly intimidating. Hidden Markov models, particle filtering, robot localization.
They sound like heavy math terms, and they are, but at their core, they're really just frameworks for dealing with uncertainty.
Okay.
It's all about how an agent, whether it's a robot vacuum or Siri on your phone, updates its beliefs about the world over time.
I love that terminology, the idea that a robot has beliefs that makes them sound almost soulful.
It's technical code for a probability distribution, but it does feel a bit philosophical, doesn't it?
It really does. So our mission today is to decode these beliefs. We're going to see how a computer goes from guessing about the weather to mapping a building, and finally, how it decodes the messy noises coming out of our mouths.
It's a journey from simple probability to complex reality.
Let's dive in.
Yeah.
So, to understand how a robot thinks, the source material suggests we start with something called a hidden Markov model, or HMM. And they use this classic textbook example. It involves rain and an umbrella.
Right. This one's perfect because it illustrates the two layers of reality an AI has to deal with. First, you have the hidden state, which we call X.
The hidden state is the truth, right? The actual reality.
Exactly. But the catch is the AI can't see it directly. So in this example, imagine you're stuck in a windowless room in some basement.
Okay.
You have no view of the outside, the hidden state, and the weather. Is it raining or is it sunny? You just can't know for sure.
So I'm the AI stuck in the basement, but I need to know if it's raining. What do I have to work with?
You have the observation. We call it E for evidence. In the slides, the observation is a security guard who walks by your office door. You can see the guard. Specifically, you can see if the guard is carrying an umbrella.
Ah, okay. So hidden state is rain, observation is umbrella. But here's the problem. Seeing an umbrella doesn't guarantee it's raining.
Precisely. Maybe the guard just likes accessories.
Or maybe they use it to block the sun.
And this is where the math kicks in. This is the sensor model. The slides give us hard numbers here. They say, if it is raining, if the hidden state is true, there's a 0.9 probability, a 90% chance that you'll see an umbrella.
That tracks. Most people, if it's pouring, grab one, but not everyone. There's that 10% factor of chaos.
Exactly. But here's the other side. If it is sunny, there's still a 0.2 probability, a 20% chance you'll see an umbrella.
So an umbrella is a strong clue, but it's a noisy clue. It's not proof.
And that distinction is why we need a hidden Markov model, and not just a simple Markov chain.
What's the difference?
A simple chain just models the state itself. Rain leads to rain, but that's useless if you're blind to the state. The HMM is the bridge. It lets the detective use imperfect evidence to deduce the hidden reality.
So the AI is basically Sherlock Holmes. It sees a wet umbrella and thinks, I calculate a high probability of rain despite not seeing the sky.
That is the essence. But it doesn't just do this once. The world changes. And this is where it gets really interesting. We enter the concept of filtering.
This was the part of the slides that really clicked for me. It describes a loop, a constant cycle. The slides call the two steps elapsed time and observe.
It's a rhythm, like breathing. In and out, elapsed time, observe.
Okay, let's break that down. Step one, elapsed time.
This is the prediction step. Before you even look at the guard today, you have a guess based on yesterday. If it was raining yesterday, it's, likely to rain today. Weather persists.
So the AI thinks yesterday was wet, so today is probably wet too. But, and I noticed this in the math, when you just elapse time,
Yeah.
their confidence actually goes down.
That's a key insight. Prediction increases uncertainty.
How so?
Think about it. If I close my eyes and try to walk across a room, my first step is confident. My 10th step, I'm wobbling. I'm not sure where I am anymore. Without new data, your certainty just degrades.
Which is why you need step 2. Observe.
Right. You open your eyes, or in this case, you look at the guard, you see the umbrella, you take that fuzzy prediction from step 1, smash it together with the new evidence, and you get a new, updated belief.
The slides walk through the math on this day by day, and the numbers tell a really cool story.
What stood out to you?
Well, they start with total ignorance, a prior belief of 0.5, 0.5.
A coin toss. A blank slate.
Then, day 1, observation umbrella. Boom. The belief that it is raining jumps to 0.82. You go from clueless to 82% sure from one clue.
That's the power of a strong sensor model.
But then they elapse time. They predict day 2, and the probability drops from 0.82 all the way down to 0.63.
The uncertainty is creaking back in. The AI is thinking, well, it was raining yesterday, but a lot can happen in 24 hours.
Exactly. But then, day 2, they see another umbrella, and the probability shoots up to 0.88, higher than the first day.
And that's the takeaway. When evidence repeats, the system becomes confident very, very quickly. It's a self-correcting loop. Predict, observe, correct.
So that works for rain. Rain is binary, raining or not. But the real world is messy.
Not at all binary.
If I'm a robot trying to figure out where I am in an office building, I'm not just here or not here. I could be 5 feet to the left, turn 30 degrees. I could be anywhere.
We call that the state space. And in the real world, it's continuous. It's infinite. If you try to do the exact math we just did for rain, your computer would just crash.
The slides call this the too big problem.
It's simply too much data to track mathematically. You can't hold a universe of possibilities in a spreadsheet.
So how do we solve it? How does the robot know where it is without melting its processor?
We cheat.
I like cheating. Tell me more.
We use something called particle filtering.
This is my favorite part of the reading because the visual is so intuitive. Instead of a math equation, the AI creates a swarm.
Yes. Instead of tracking a perfect probability curve, the AI just says, okay, I can't track everything, so I'll create thousands of little guesses. We call these particles.
So imagine a floor plan. The robot doesn't know where it is, so it just throws a digital handful of thousands of red dots all over the map.
Exactly. At the start, it's global uncertainty. There are dots in the hallway, dots in the break room, dots inside the walls. Each dot is a hypothetical robot.
And then we run that same loop. Elapse time, observe. But there's a new third step, resample.
Let's walk through it. First, elapse time. The robot moves its wheels 1 meter forward.
So the AI takes all those thousands of dots and just slides them all 1 meter forward.
But remember, robots are janky. Tires slip. So we add noise, we jiggle the dots a little, they spread out, representing that loss of confidence.
Step 2, observe. The robot uses its sensors. Let's say a laser pings a wall 2 meters in front of it.
This is the moment of truth. The AI looks at its swarm. It goes to each dot and asks, hey, if we were actually standing where you are, would we see a wall 2 meters away?
And if a dot is standing in the middle of a long, empty hallway where the nearest wall is 50 meters away?
Then that dot is clearly wrong. It contradicts the evidence. It gets a tiny weight, say 0.0. It's a bad guess.
But if a dot is standing exactly 2 meters from a wall on the map?
That one matches reality. It gets a high weight 0.9. It's a good guess.
And then comes the magic trick. Step 3, resample.
This is basically evolution, survival of the fittest. The algorithm draws a new generation of particles, but it draws them based on those weights.
So the good guesses, the heavy ones, get picked multiple times. They get to clone themselves.
And the bad guesses, the ones that thought they were in the hallway, they don't get picked. They die off.
That is ruthless. It's like the Hunger Games for data.
It's efficient. After just a few cycles of moving and sensing, you look at the map and all those scattered dots have vanished. They've clustered into one tight little cloud right where the real robot is.
The swarm converges on the truth.
That is robot localization. It's incredibly robust. Even if the robot gets kidnapped, picked up, and moved, the particles eventually figure it out.
But wait, the slides raise the stakes even higher. In that example, the robot has a map. It knows the floor plan.
Right.
What if you drop a robot into a burning building?
Parker.
Or a cave on Mars. No map, no GPS, nothing.
Ah, the holy grail of robotics. SLAM.
Slam, it sounds like an action movie.
Simultaneous localization and mapping.
That sounds impossibly difficult. You have to figure out where you are in a map that you're drawing at the same time.
It is a classic chicken and egg problem. To draw the map, you need to know your location. But to know your location, you need a map to compare your sensors against.
So if you're wrong about one, you're wrong about everything. The errors would just stack up until the map is a total mess.
Exactly. In this case, the hidden state isn't just your location. The hidden state is the location plus the map itself. The complexity just explodes.
The slides mention things like DP slam and Kalman filtering. How do they even solve that?
By not committing to one chicken or one egg.
What do you mean?
Remember the particles. In SLAM, each particle isn't just a location. Each particle carries its own personal map.
Wait, so you have thousands of dots and each one has a different opinion on what the building looks like?
Yes. Particle A says, I'm here, and the hallway is straight. Particle B says, I'm 2 inches to the left, and the hallway curves.
Wow.
As the robot explores, the particles that draw maps consistent with the sensor data survive. The ones that draw nonsense maps die out.
That is mind-blowing. There's this great illustration in the slides of a robot holding a flashlight, surrounded by what looks like ghosts.
I love that image. The ghosts are the particles. The robot is constantly fighting off the ghosts of incorrect probabilities to find the one true reality.
I feel like I'm doing that on a Monday morning before coffee, just fighting off ghosts of where I think my keys are.
We all are.
So we've talked about robot eyes lasers, cameras. I want to pivot to ears, because it turns out this same math HMMs is exactly how we solve speech recognition.
It's a beautiful connection. Whether you're navigating a hallway or decoding a sentence, the math is shockingly similar.
The slides start with the physics of sound.
Mm.
And I never really thought about my mouth this way before. They describe the vocal tract, your mouth and throat, as a tube.
That's effectively what it is, an instrument. When you speak, you're pushing air through this tube. And depending on how you shape it, where you put your tongue, how you open your jaw, you change the resonance frequencies.
So an ah sounds different from an e, because I'm changing the shape of the tube, which amplifies different harmonics.
Exactly. And that sound comes out as a waveform. The computer samples this, usually about 16,000 times a second.
But the computer doesn't just look at the raw squiggly line, right?
No, way too messy. It converts it into a spectrogram. Think of it like sheet music for a computer. It shows where the energy is, low pitch, high pitch over time.
Then it slices that sheet music up.
Right. Every 10 milliseconds or so, the computer takes a slice and turns it into a list of about 39 numbers. We call them acoustic feature vectors.
Okay, so we are back to numbers. The observation was the laser reading. Here, the observation is this list of 39 numbers.
Correct. And the hidden state, X, that's the foam, the actual unit of language you're trying to say. The P in particle or the S in speech.
So the computer has this list of numbers and has to guess what sound caused this.
Yes. But just like the umbrella, it's not perfect. A P sound might look a lot like a B sound in the data. They look very similar on a spectrogram.
And this is where the HMM comes back. Because language has structure, it has transition probabilities.
Exactly. If I hear a sus sound, there's a high probability the next sound is a P or a T. A very low probability the next sound is a Z. The HMM knows which sounds flow into each other.
The slides use the example of the phrase speech lab, and you can see how the HMM tracks it. It's not just guessing one sound at a time, is it?
No, and that's the critical part. If you just guessed every millisecond separately, you'd get gibberish. You'd get SSPBEF.
So how does it smooth that out? How does it know I said speech lab?
It uses the Viterbi algorithm.
This sounded like the final boss of the speech section.
It's actually very elegant. The Viterbi algorithm doesn't just look at the current moment. It looks at the whole sentence at once. It asks, what is the single most likely path through this forest of sounds?
So it's looking for the storyline that makes the most sense.
Exactly. It's comparing speech lab versus peach slab. Maybe locally, the P sounds a bit like a B. But globally, the Viterbi algorithm finds the path that maximizes the total probability given all the evidence.
That's fascinating. It's basically autocorrect, but for raw sound waves.
And that leads us to the bigger picture. The slides end by zooming out to something called dynamic Bayes nets, or DBNs.
Yeah, this looked like the generalization of everything we've talked about.
It is. An HMM usually tracks one main hidden variable-like location. A dynamic Bayes net lets you track multiple variables over time, all influencing each other.
The visual showed these complex webs of nodes repeating over time.
Think about a self-driving car. It's not just tracking its own location, it's tracking the car in front of it. That car has a position, a velocity. But wait, the traffic light is also a variable. And the pedestrian on the corner.
And they all interact. If the light turns red, the car in front slows down, so I need to slow down.
Exactly. A DBN allows us to model that entire complex web. It's the structure used for the really heavy lifting in AI.
It's basically acknowledging that the world is messy and everything is connected.
And that, despite the mess, we can use probability to tame it.
So let's wrap this up. We started with a simple question about a security guard carrying an umbrella.
A simple clue that unlocked the concept of hidden states.
We moved to a swarm of particles helping a robot find its way through a hallway.
Solving the too big problem by letting the bad guesses go extinct.
And we ended with the Viterbi algorithm decoding the vibrations of air into human speech, finding the best path through the noise.
And the thread connecting them all is that machines don't deal in certainties. They deal in belief states. They have a distribution of possibilities, and every bit of evidence just shifts that distribution slightly closer to the truth.
It kind of changes how you look at the world. We like to think we see reality exactly as it is, but our brains are just biological computers processing sensory inputs.
That's a valid point. We have our own sensor models. Our eyes have noise. Our memories have noise.
So here is a provocative thought to leave you with. We talked about how the robot uses particle filtering, throwing out thousands of guesses to figure out where it is.
Right.
Are we doing the same thing? Is your brain currently running a massive particle filter? Are you unconsciously swarming thousands of different realities in your head every millisecond and just collapsing them down to the one that makes the most sense?
That's actually known as the Bayesian brain hypothesis, the idea that perception is just a controlled hallucination that best fits the data.
So is a reality you see just the surviving particle?
If the ghosts converge, does it matter if it's a hallucination or reality?
I don't know, but I'm going to need a minute to process that belief state. Thanks for listening to The Deep Dive. Keep your probabilities updated, everyone.